Buddy. I wanted to talk about the disk method from calculus. Um, so first I want to go over the idea and then we can do a few examples. So supposing we have a function y equal to f of x and we want to find the volume of the solid generated when we rotate this function about the x-axis. Now, when you were doing Riemann sums, the idea was you had rectangles and you added up the area of all the rectangles and you found the area under the curve. Well, when you're using the disk method, it's very much like a Riemann sum, except for instead of rectangles, what you're summing up is disks with a little tiny bit of thickness. So let's say we are at this point, x comma f of x. And we'll say we have a disk. We're using left endpoints. It's not particularly important because we're not actually going to do the Riemann sum. It just helps you visualize what's going on here. At any rate, so then we get a disk, and the disk looks something like the following. And this disk has a little bit of thickness like that. And I'll just go ahead and erase this. It makes it look more three-dimensional. And we say the thickness of this disk is delta x. Okay, well, so if the radius here is f of x, and the thickness here is delta x, we know from the formula for a cylinder that a little piece of the volume of the solid generated by rotating this region about the x-axis delta V is going to be the area of the disk, which is pi, and then our radius here, which is f of x squared times a bit of thickness here, delta x. So usually when we're dealing with cylinders, you see it the other way. So let me just go ahead and draw this again. Okay, so here's our cylinder. Right here we have our radius. And that is f of x. And we have the height of our cylinder, which is delta x. And just in general, the volume of a cylinder is pi r squared h. So like I said before, the radius is f of x, the height is delta x. And because we're not talking about the volume of the cylinder, but the volume generated by the entire shape, it's delta x, delta v in our case. So this is going to be delta v is pi f of x squared delta x. Okay, and now what happens is we sum up all of these delta v's and we get the total volume. Well, actually not quite the total volume, because there's going to be a finite number of these, and of course we would need delta x to be infinitely thin for it to add up. However, as the thickness delta x goes to 0, this approaches the actual volume, and of course from the limiting reasoning that we learned from calculus earlier, we get that v is going to be the integral of pi f of x squared dx. And because we're going from a to b, this is going to be integral a to b. Okay, let's try some examples. Problem is finding the volume generated when the region bound by the x-axis, x equals 1 and y equals x squared, is revolved around the x-axis. So I like to start by drawing what one disk looks like in this situation. So let's suppose we have a disk like so. And then I'll erase it. It's not perfect, but that's fine. And then the thickness here is delta x, and we have the radius here. It's a little bit hard to see, that's x squared. Okay, so a little piece of volume delta V is going to equal pi times the square of the radius, and we said the radius was x squared, so x squared squared times the horizontal length here, delta x. Okay, this of course implies that the entire area V, I'm going to bring the pi outside of the integral. X squared squared, that's x to the fourth, dx. And then the integral is from 0, because that's where it intersects that's when y equals x squared intersects the x-axis at 0, 0. And then over here, this is 1, 1. So this is going to go from 0 to 1. Okay, so now all that's left is to go ahead and work this out. V is pi times the integral from 0 to 1, x to the fourth dx. All right, so now what we do is we add 1 to the power, divide by the new power. That's the power rule for integrals. And of course, our bounds of integration are 0 and 1. And then we plug in the top and we subtract the bottom. So this becomes 1 to the fifth over 5 minus 0 to the fifth over 5 1 to the fifth is, of course, 1. 0 to the fifth is 0. And any number divided by 0, or 0 divided by any number is 0. One-fifth minus 0 is 1/5. And we can go ahead and drop the brackets. Okay, pi times 1/5. Pi is, of course, the same thing as pi over 1, and when you're multiplying two fractions, you just multiply the numerators. Pi times 1 is pi. 1 times 5 is 5. And that is the volume generated by this guy. You can kind of visualize it. It's like a cone shape, except for it's concave inward. So the shape would be something like the following. And then it has circular cross sections, like so. And we just proved here. No, it goes the other way. And we just proved here the volume of this weird shape is pi over 5. Okay, our next problem. What is the volume of the solid generated when the region bound by y equals tangent of x equal pi over 4, and the x-axis is revolved about the x-axis? So just drawing an arbitrary disk here, we have something that looks like this. And there's a little bit of thickness, delta x, and here is our radius. And that's the length from the x-axis to y equals tangent of x, so that length is tangent of x whenever tangent of x is positive. Okay, so now a little chunk of volume here, delta V is going to be pi times the square of the radius. The radius is tangent of x, so it's going to be tangent of x squared times a little bit of thickness delta x. So this implies that the total volume V is pi times the integral of tangent squared of x dx, and because x goes from 0 to pi over 4 in our region, the lower bound of integration is going to be 0. The upper bound of integration is going to be pi over 4. All right, now the next question here is, how do we deal with tangent? It's actually not too tough, but a lot of students don't know how to handle it. So the way that we approach this is the following. We know that 1 plus tangent squared x is equal to secant squared x. This is a Pythagorean identity. And of course, if 1 plus tangent squared x equals secant squared x, that implies the tangent squared x is equal to secant squared x minus 1. Okay, so now we're going to use that here. We have that v is going to equal the integral from 0 to pi over 4 of secant squared x minus 1 dx. Okay, and let's just box this off and we'll go up here to finish off the integral. Okay, v is pi times the integral from 0 to pi over 4 of secant squared x minus 1 dx. Okay, now from here, it's mostly just a matter of memory. The antiderivative of secant squared x is tangent x. Easier here, the antiderivative of 1 is simply x. And this is going to go from 0 to pi over 4. Okay, now we're just going to plug in our bounds of integration. It's going to be top minus bottom. So we have tangent of pi over 4 minus pi over 4 minus tangent of 0 minus 0. Okay. Tangent of pi over 4 is simply 1. Pi over 4 just stays put. Tangent of 0 is 0, and then 0 minus 0 is 0. And once again, we have 1 minus pi over 4 minus 0, so we anything minus 0 is just that thing. So this is going to be 1 minus pi over 4. I'm going to switch to parentheses. And there is our final answer, pi minus the difference of 1 and pi over 4.